Welcome to the structural analysis course. So in the last two class before, we have started the new topic, that is how to calculate the deflection and slope into a beam. And in the last class we have derived the beam equation. So today we'll start our first method to determine the slope and deflection in any beam. So this first method today we'll discuss, that is the double integration method. So let's get started. So if you recall, last class we have derived the equation of a beam. So if you recall, this is the equation we have derived, right? D square x d square x dx square equal to m by ei. So now if you now can you tell me what is m? So if you recall, m we discussed is the moment, right? And e is the modulus of elasticity of a beam, and I is the in moment of inertia, and you have the deflection at any point is y, if you recall. So this is the equation we have derived in the last class. So just quickly I'll just recapitulate what we discussed. So just take consider this is arbitrary beam which is a simply supported beam, right? One end is a hinge, another end is roller, and you have some arbitrary loads acting on it. Maybe some UDL is acting, or maybe some point load also may be acting at different location, different position. So you can consider this is any arbitrary beam with some load is acting on it. So after application of the load, what will happen? As we saw in the earlier lectures, so when the load is applied into a structure, then our internal stress or internal forces will generate inside the beam, right? What are the internal forces? So we have the internal forces. One is bending moment, shear force, right? Or the stresses. All these things are actually internal force generated. So the beam is a bending member, right? So when the transverse loads are acting on a beam, so this is the moment. Maybe some moment will be generated inside the structure, right? So this is the convention, sign convention we will use for this entire course. So after application of the load, our beam will buckle, right? So this is a buckling shape of a beam, although this may not be, it is an exaggerated manner, and this is, we call it, is a deflection y, right? And what is slope at any point is just draw a tangent at any particular point, and which makes, what is the angle it makes with the horizontal, right? If you next, if you draw, so how much angle it makes with the horizontal. So this is the horizontal, right? Theta. So at this point you have the slope theta, whereas deflection maybe at this point you have a y1, right? So in every point or on a beam you will get two unknown parameters. One is deflection. At any point you will have a different deflection. If you are measuring, and at the center of the beam you may get higher deflection, but if you measure the deflection at this point you will get lesser deflection. So, and another thing is you will get the slope. So at any particular point on a beam, you will get two unknown parameter, or two parameters. With one is deflection, means how much deflection takes place from the original position after application of the load, and second one is the how much is the slope. What is slope? Slope means at any particular point you draw a tangent, and that tangent, how much angle it is making with the horizontal. That we call it theta, right? So two parameters. Our main objective in this module would be to find it out what is the slope and what is the deflection at any particular point of a structure. So both the parameters are very much important for us to understand, because when you design a structure, so that we have to check the deflection of a beam should not be too high. It should be in a particular limit, in a permissible limit, right? So for example, if you are sitting on a floor, right, and some people or some student went, sat in the first floor, just above your head, like above your head one floor will be there, right there. If 60 student came, so after the 60 student enter into the class, suddenly load has increased in the slab, right? So so because of this load, if your slab deflects excessively too much, maybe the deflection, although in every case we'll have some deflection, but normally by naked eye we can't see how much deflection takes place. But if deflection is too much, too high, maybe 10 centimeter or 15 centimeter. It is very 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 high deflection. In that case you will feel panic, right? You may think that anytime the slab may collapse in your head. So that's why we have to find it out after application of the load how much deflection should takes place. So if the deflection is into in a permissible limit, then we will tell yeah, this design is fine, this design is okay, deflection is in the limit itself. Otherwise you have to redesign the structure. So that's why to calculate the deflection and slope is very much crucial in structure analysis. So that's what we discussed. So today in this method, in this double integration method, basically we'll find it out how exactly you can calculate the deflection and slope at any point on a structure, right? Okay, so we have derived this equation. If you remember, d square y dx square equal to m by ei. What is y? Y is the deflection at any particular point. Y is a variable, right? Here we have derived the equation in a derivative manner. So y is the deflection at any point, which is a variable. Similarly, x is the distance from any point, right? X also a variable, and m is the moment at that point, at any point where we are finding out the deflection, that we call it m. And then you have the ei. E is the modulus of elasticity of the beam material, and you have the I is the basically the moment of inertia of the beam, right? And this is the sign convention basically will follow here. So what is the sign convention? So always deflection not towards up, will consider it as a positive deflection. Okay, and you have the theta also. If it is anti-clockwise, positive theta means the deflection will be anti-clockwise. Means I'll just let me draw here. So if a beam, so consider a beam. So this is a simply supported beam. So one end is hinge, another hand is roller, right? And some load is applied, UDL. Maybe consider. So because of that, you have the deflection, right? So deflection. Now if you draw a tangent at any particular point, so let's draw, this is a tangent, right, at this point. So this tangent makes angle with horizontal, maybe theta. So this theta is anti-clockwise, right? If you so we are bending from anti-clockwise to from the axis, right? This is a positive theta, so that's what we considered. Okay, and so this is very much important to understand here. And another very important thing is the slope. So slope, if you recall, in the last lecture we discussed for different support cases what could be the theta, I mean what could be the slope. So this is a hinge support, right? Hinge support means it has two reactions. So one is vertical reaction, another is horizontal. So you have one vertical reaction and there will be horizontal reaction. So two reactions you will have. So there is no moment, right? There is no moment reaction in the hinge end support. So that's why the deflection will start from the support itself. So here it is 0, but if you see the slope started from here itself. So at the support, the slope is not 0. You will have some value, right? If you draw a tangent at this point, still you will get some value. Very high slope, maybe you will get it here. But if you consider this is a fixed support, so then the slope fixed support has three reactions, right? One is vertical, one is horizontal, and you have the as well as fixed end moment also. So once you have the fixed end moment, so that's why deflection won't start from here. So deflection may start from after some time. So that's why you will get the slope at the support is 0 in case of fixed support. Whereas in the hinge support, you will have some slope at the support. Even for the roller case also, you will have some support. Right? These things we discussed in the previous lectures. Right? So this is the equation we have derived in the last class, d square y dx square equal to m by ei. So our main objective is what? Our main objective is to calculate the y. Y means deflection, and theta to calculate deflection and slope. That is our main objective, right? So y is theta, so y is the deflection. So how can you find it out y from this equation? Right, this is a double derivative of y is m by ei that we derived in the last class. So from here, how can you find it out y? So we have to integrate the equation, right? So if you integrate it, so integration, right, d square y by dx square equal to m by ei. So ei, here also you have the integration. So once you integrate, what will happen? So you will get now d square dy dx, right? So so after integration, so they will get m by ei, right? So after first integration, you got this expression. So after first integration, you got dy dx equal to m by ei. But our main objective is to find out y, right? Our main objective is to find out y. So y means you need to integrate one more time. So integrate again. So again you integrate. So what you will get? You will get now y equal to double integration m by ei. So that is the one y. Y means deflection. So that's why the method name also called double integration method. Basically, we are integrating two times. That m by ei, we are integrating two times, and then you are getting the deflection, right? M by ei, where two integration, two times integration. If you do, then only we will get the m by ei, right? So originally it was double derivative. So if you integrate two times, basically you are releasing the y. Now you have the y is equal to this much. So this is the deflection. Now can you tell me what is slope? Right, so what is the slope? Slope means, as I mentioned, it is a tangent, right? Tangent, the slope, tangent at particular point. What is the slope? So dy dx is a derivative, right? That is the slope. We know at any particular point dy dx is basically will give you the slope theta. Okay, let me just explain it in a more detail. So just consider a beam here, and you have roller fixed sorry hinge one end and roller one end, and after application of the load, this is a deflected shape, right? So at any particular point, if you want to find it out the slope, so this is a slope, right? So this slope is theta with the horizontal, how much angle it is making. So this, with the horizontal, how much angle, I mean, that is a theta, right? So how much will be the slope? So if this so just to draw a triangle, so this small triangle, basically I'm drawing it separately, right? So sorry, so this is the theta angle, right? So this angle is theta. So our main objective will be to find it out what is the slope theta. So this small area is basically your dx, and the height means deflection area, right? Dy. So what is theta? So basically tan theta is equal to dy dx, right? So, but the normally the slope is, if it is very negligible, then we can call it theta is equal to dy dx. So ultimately theta, so dy dx, whatever you will get, dy dx, so first derivative, so this one is basically your theta. So what you get now? So let me write it clearly. So from here, if you integrate first integration, if you take do it for this equation, you will get dy dx, right? So dy dx is equal to integration m by ei and plus c, right? What is c? If you integrate, always you will get the integration constant also, right? So this c, so this dy dx is nothing but a theta. So this is actually theta. So, and again one more time, if you integrate, then you are basically releasing the y. So y is equal to double integration m by ei plus c1x plus c2. So what is c1 c2? C1 c2 is nothing but a integration constant. So c1 c2 is nothing but the constant of integration. So what you get ultimately, so this is your main equation. If you integrate it one times, you will get it dy dx. Dy dx is nothing but theta. So this is our theta, you get it. And again if you integrate, you will get y. So y is our deflection. So when you integrate these two times, basically you are introducing two constant in the equation, c1 and c2. So two constants you have. So how to calculate, how to find out this constant value c1 and c2? By applying the boundary and continuity conditions. So we have to apply now boundary conditions to calculate the c1 and c2 value. So what is boundary condition? Boundary condition means at boundary, if you see what is the value. So at boundary means at this point, what is the deflection? Deflection at this point will be how much? It will be 0, right? So similarly, what is the deflection at C? And in this support, it is also 0. So that's what the two have we have the two boundary conditions, right? So y equal to, y means what? Deflection at A equal to 0, right? So this y value should be equal to 0 when x value is also 0. So x is a variable starting from here. So here x equal to 0 and here x equal to total length of the beam. Maybe it is L, right? So when x equal to 0, you have y equal to 0. So from here, you can calculate when you get one equation, and another equation from here you will get, right? At x equal to L, total distance, what is the y? Y is also equal to 0. So plug in both the values in this equation, you will get another equation. So from these two equations, you can easily compute what is the value of C1 and C2. And your computation of theta and slope, theta and deflection is complete. So now let's see the procedure analysis. So what first you have to do? What is the first step? So let's discuss about the step by step how exactly you will solve the problem. First, you have to draw the elastic curve. What is elastic curve? So beam may be given in any shape. So for example, maybe a simply supported beam, and maybe some loading is there. UDL point load, again UDL, something maybe is given. Any arbitrary load may be given. So in that case, your first job will be to draw the elastic curve. So this deflected curve, we call it elastic curve. So our first job will be just looking into the supports and support condition and all. We have to draw the elastic curve. Okay, so this is obviously in exaggerated manner we have to draw, but in reality maybe deflection may not be happening that much. In reality maybe deflection is very small, but for analysis purpose we will draw in exaggerated manner, very high deflection will draw. That is our first step. So once you draw the elastic curve, next we have to find it out the moment equation. So already we know in the last lessons we discussed how to calculate the moment at any particular point, right? So in this beam, at any point you have to calculate what is the moment. So once you know the moment equation, then you just plug in this equation. So we have our beam elastic equation, right? d square y by dx square is equal to m by ei. Just substitute whatever moment equation you got it, and you integrate it two times. You will get theta, and you will get deflection and slope both. And then you apply the boundary condition to calculate the constant C1 and C2. So these are the basically three steps you have to follow. First one is draw the elastic curve. Next one is draw the, find it out the moment function. And lastly, you have to draw, lastly you have to plug in the moment equation in the beam equation, moment function into the beam equation, and integrate it two times. In first integration, you will get the slope. Second integration, you will get the deflection. And then so when you integrate it, you will get two integration constant also, right? So this both the integration constant, again you would substitute the boundary conditions in that, and you will get the C1 and C2, means all the constants also you will get it. So let's solve a quick problem, then the entire concept will be clear to you. So this is example: determine the slope and deflection at point B. So what is it at point B of a cantilever beam shown in a figure? So this is a figure, it is shown by the direct integration method. So this method is called direct integration method. Also sometimes it is called double integration method, because two times basically we are integrating, right? So that's why we call it this method as a double integration method also. Okay, the question here is, so this is a cantilever beam given to us. So just recall, cantilever beam means you have one end is fixed, another end is free, right? So this is a cantilever beam, and one load is acting 15 k. K means kip, basically it is kilo pound, that is F in FPS unit, the system is given, right? Fit and kip. K means kilo pound. Anyway, so 15 k is acting at the tip of this cantilever beam here, and the total length of the beam is given to us as a 20 feet. EI value also given to us. EI is constant. E value also given to 29,000 KSI, right? So this is our beam. So what is our first job? So if you recall, our first job will be to draw the elastic, elastic elastic curve. Elastic curve means basically the deflected shape. So after application of this load, how the beam will deflect. So if you just draw it, so something, this may be the deflected shape, right? After application of the load, this beam may deflect in this dotted line, in this line, right? In this blue line, the beam may deflect. So that is our first job. So what is the question? Question is, you have to find it out what is the slope at deflection at B. So means at this point, right? And this is the elastic curve we have drawn. Just by looking into this is a curve we have drawn. Now if you would see, this is a fixed end supports, right? Fixed end support means, that's why the slope or the deflection not started from the support itself, unlike other two. So just I'll draw it for the hinge support also. For the hinge support, if you recall, last slide also we have drawn. So you have a hinge and roller, and if some load is acting on it, then the deflection always starts from the support itself. So the deflection started from the support itself, right? But here, if you see in the cantilever beam, so this cantilever beam deflection did not started from the support itself. Deflection started after sometimes this deflection started. Why? Because in the cantilever support you have the three moment, right? One is horizontal reaction, one is vertical reaction, another is a fixed, and moment is also there. So because of this moment you get zero deflection and zero slope basically at the support. So that's why this is a deflected shape. So you are asked to find out what is the deflection happened. So this height, what is this height? So this is the thing we have to calculate. So we have to calculate this height, right? This is y maybe. And what is the slope at b? Slope means what? So in the elastic curve, you have to draw a tangent. So this is a tangent at the elastic curve, and this tangent, how much angle it is making with the horizontal. This is theta. So these two parameter basically we have to find it out. One is deflection at this and this tip end, deflection at this b, because it is given right at point b, you have to find it out. So y and theta also means what is the slope at this point, you have to find it out. So our first step is over, that is drawing the elastic curve. So our next step will be to write the moment equation. So moment equation, so let's do it quickly. So how can you do that? So let's consider our variable x started from a. Okay, let me do it here. So our variable x started from the support itself. So from here you have the x, right? Now what will be the moment at any point? So if you could draw at any, maybe at a distance of x, let's consider this distance is x, right? So up to this you have the x. So what is the moment at this point? Mx at a distance of x. How much will be the moment? So can anyone do it quickly? Moment is how to calculate the moment. So how to calculate the moment? So what is the reaction? First, our first step will be to find out the reactions, right? So only one vertical force is acting downward, right? 15k. So 15k is acting downward. That means you have the reaction here at the support. That also you have the 15k, which is upward direction, right? This is a single reaction you have. So now if you are finding out the moment at this point, then moment will be how much? What is force into distance, right? So only one force is acting in this left side, 15. So you will have a 15 into distance, right? Distance is how much? Or maybe in right side you can consider. So this is the load, 15 is acting, and what is the distance? The distance is this entire this distance, right? So what is this distance? So total is 20 feet. So let me write it. It is 20 minus x, right? This is the distance. Okay, so let me just explain here. So at this point, basically, we are finding out the moment mx. So mx will be how much? So now let's consider the right side. You have only single force. It is 15k is acting downward, right? So 15k is acting clockwise direction. So if you see, this is a clockwise direction. So 15k is the force. Force is 15 into distance. The distance is from here to here. How much is the distance? So total distance is given to us, that is 20 feet, and this distance is we considered x, right? Our x variable starts from the support. So this is x, and this entire length is 20, right? Then how much from here to here? So it is 20 minus x. So you have the force 15 and distance is 20 minus x. So 15 into 20 minus x is the total moment at this point, mx, right? And this moment is acting which direction? Clockwise direction. See, it is clockwise direction. So as per our sign convention, clockwise we consider it as a negative. So negative. So whatever moment we got computed now, so it is minus 15 into 20 minus x. So that's what we have written here. That is moment with respect to x variable minus 15, 20 minus x. So this is a moment at any particular point. X is a variable, right? X may be here, here, at any point of a beam. This is the equation. Just substitute the corresponding x value, you will get it. So this is the moment equation. Now we computed our step 2 also. Step 1 was to draw the elastic curve. This blue color line we have drawn, and we identified we have to compute the value of y and theta at point b, right? That is a question given to us. Next step was we computed the moment minus 15 20 into 20 minus x. So moment is nothing but a force into distance. Force is 15 into distance is 20 minus x. So this is a moment. So now we have the beam equation which we derived in the last class. That is d square y by dx square is equal to m by ei. So this is the expression we have derived in the last class. So let's substitute the value of moment here. So moment already you know, this is when you computed. So substitute it. So 15 into 20 minus x by ei minus. So this is the substituted. So now if you take the derivation, first derivation, so that is dy dx, you will get it. First integration, sorry, first integration, you will get dy dx equal to minus 15. This is a constant, right? 15 is constant anyway. Ei also constant given to us, right? Then what is the integration of 20? Integration of 20 will be 20x minus integration of x will be x square by 2, x square by 2 plus c1. So what is c1? C1, as I mentioned, it's a integration constant. So once you integrate a equation, you will get a constant, right? There is an integration constant c1. So this is our first after you do the first integration, you will get dy dx, which dy dx is nothing but a theta, means slope. So this is a slope, we got it. Now similarly, if you integrate one more time in this equation, because our main objective is to find out theta and y. So if you do integrate it one more time, so you will get y now. And if you integrate this entire part, so 15 by ei is anyway constant, it will be outside. And then 20x, what is the integration of 20x? So x will be x square by 2, right? That means 10x square minus x cube. Integration of x cube will be what? X square will be x cube by 3. So x cube by 3 into 2, 6 came, plus integration of constant c1 into x plus c2. One more constant came because two times you are doing the integration, right? So now these two, theta and y. So this is our main objective to find out. But if you see, we have the constant also, c1 and c2. But we do not want c1 and c2. We want some value, right? So how to compute the c1 and c2? So we have to employ the boundary condition. What is boundary condition? Boundary condition means at a, what is the slope? At a, slope is 0, right? Because deflection started from here. So if you draw a tangent at this point, it will be simply horizontal, right? So slope at a is also 0. So that's what the slope at x equal to 0, theta is also 0, right? At x equal to 0, x starts from here, right? Here x equal to 0 and here x equal to 20 at this point. So at x equal to 0, you have theta also 0. This is one equation you got. And another equation, what is the deflection at a? Deflection at a is also 0, right? Because it is a support, so there should not be any deflection at a. So that's why the boundary condition at x equal to 0, y is equal to also 0. So you have the two equation. At x equal to 0, you have the slope equal to 0, theta equal to 0, and also at x equal to 0, you have the y, that is deflection also equal to 0. So you have these two equations. So just plug in at x equal to 0, theta equal to 0 in this equation. So in this equation, just substitute at x equal to 0 means here this term will go 0. This is also 0 because x value is 0 and theta value also 0. So what you will get? C1 equal to also 0. Just do it and you will get it, the equation, right? And next, so c1 you got now 0 from this first equation. Now substitute this one at y equal to 0, x equal to 0. So here, so y equal to 0 now and x equal to 0. So x equal to 0 means this term will go away, this term also will go away, this term will also go away. So c2 is equal to also 0. Right? These two points basically we are substituting in both the equations and we got c1 and c2 both are equal to 0. So now what is the final equation then? So final equation will be theta is equal to minus 15 by ei into 20 minus x square by 2. C1 is anyway 0. So this is our theta. And what is y? So y is nothing but the c1, c2 both are 0. So remaining part y will be only this part. So this is y. So deflection at B. So now question asks to find out what is the deflection at point B. So point B means at this point. So in this point, just substitute what is the x value here. So x is 0 at this point. But what is the x at this point? It is 20, right? Total length is 20. So just substitute here x equal to 20 and find out what is the value of theta. So this theta will be theta b. So just and then you will get this is the value. Similarly, just substitute at x equal to 20 what is the y. So y you will get it. This is the value. So minus 3.14 inch. So after application of 15K, you will get deflection at this point is 3.14 inches. That is YB. So now if question says at any point, if you find it out what is the deflection at midpoint of the beam. So midpoint means what? X equal to 10 now. So just simply substitute x equal to 10 in this equation. You will get what is theta and what is y at the midpoint. So like that in any point, just simply putting the value of x, you will get it. What is the value of theta and what is the value of y. Right? So that is the advantage of using double integration method. It will give you the slope and deflection with respect to x. X is a variable, right? If you just substitute x any value at any location of a beam, you will get the final theta and phi. Okay, thank you.